Now, up until this point, we've talked about capacitors which just have an air gap space in them. You've got a positive conductor, a negative conductor, and we keep them a certain distance apart, and charge will build up on each plate. We can enhance the capacitance of a capacitor by putting a material such as a dielectric between the two plates. And the great thing about this is the dielectric not only acts to enhance the polarization of the plates, it reduces the amount of voltage that we need to have for a particular charge stored. Okay? Dielectrics in most cases are actually very, very good insulators. So we can rewrite our equation. Original equation for the air gap capacitor was the capacitance was equal to epsilon 0 A over D. Now we add this constant right here, this kappa, and this is the dielectric constant that is completely dependent on the material that we put between the two plates. And sometimes we use a material with a high dielectric constant just to make the capacitance very, very large. Sometimes we'll use a material that doesn't have as high of a dielectric constant, but has really good insulating properties, which will allow us to actually go to higher voltages than normal. So again, here is our capacitor, a parallel plate capacitor, and the voltage that we have across it given some charge Q. Now putting a dielectric across this, the dielectric polarizes, and for the same amount of charge, the voltage is actually reduced. Remember, capacitance is the amount of charge you get for a given voltage. So for instance, if our dielectric constant is 2, I can store twice as much charge for the same voltage, or have half the voltage to store the same amount of charge. And again, if you were to suddenly place a dielectric in between these two plates for a given amount of charge, you would notice a voltage drop. This, in fact, is the principle behind different devices that we use to detect materials behind sheetrock. Once you put sheetrock up and it's painted, you don't want to put unnecessary holes in it. But if you want to hang a picture, you want to make sure that you're drilling into a piece of wood, what we call a stud. And we use these stud finders to actually detect the dielectric difference between where it's hollow behind the sheetrock compared to where there's wood, because wood has a higher dielectric constant than just air. So dielectric strength tells us how polarizable the material is. And again, for a given plate separation, there's a maximum electric field that this dielectric material can stand before we tear the covalent bonds apart. And we call this the dielectric strength. Before putting too much voltage across it will cause the capacitor to fail. And here we see different materials with different dielectric constants. Here's air. Its dielectric constants, for all intents and purposes, is 1, and then different materials and what their dielectric strength is. So for instance here, strontium titanate has an excellent dielectric constant. You can get 233 times as much charge for the same voltage. However, you notice that its dielectric strength at 8 times 10 to the 6th, high, but there are other materials that are much higher. That means if you're only a millimeter apart, the best you can do is put about 8,000 volts across it. Okay? Compare that to a material like bakelite. Bakelite, not as high in terms of its dielectric constant, but able to take 3 times the amount of voltage. So again, here's some different materials. Teflon, very high dielectric strength, only 2 for dielectric constant. So that would be good for very thin type capacitors where we want to insulate at very, very small distances. Actually, water has a very high dielectric constant, as you might imagine, but not really used for capacitors because it's very difficult to keep the water pure. any small amount of electrolyte in there is going to make it conductive and basically short out your capacitor. So again, here is our parallel plate capacitor. We're going to calculate the capacitance. Again, we have an area of 1/100th of a square meter. That's the same area that we used for the earlier example. But now we're going to use a piece of quartz in between it, and quartz has a dielectric constant of 3.78. So when we calculate the capacitance, we see that we actually get a higher capacitance, well, 3.78 times greater than what we got in the earlier example in the first section. Now, when we look at real capacitors, we see real capacitors typically don't look like two big plates. Most capacitors will look like cylinders or they'll look like buttons. The cylinders are usually the highest capacity capacitors. And there's a metal foil that becomes the positive plate. There's a piece of metal foil that becomes the negative plate. And this is rolled up into, like a huge, roll of paper towels. And this is rolled up to take all that area and compress it into a much smaller volume. And we use some type of dielectric material to insulate it, okay? Could be paper, could be Teflon, could be a number of different materials, plastics, but it allows us to reach a much higher area and therefore greater capacitance. And again, here's some different capacitors. You can see the cylindrical ones. These are the ones with a much higher capacitance. Some smaller cylindrical ones, some button-shaped ones. The button-shaped ones are interesting. They actually have a helical winding of wire, which creates there's a positive wire and there's a negative wire, and they're more for precision than they are to actually store a tremendous amount of charge. This is an air gap capacitor. These were very, very important for tuning radios. Radios are basically what we call RLC circuits. There's resistance in them. There are inductors, which are basically electromagnets, and there are also capacitors. By adjusting the capacitance, we can adjust the frequency at which the radio is going to amplify in terms of radio waves. So again, here's our cylindrical capacitor. This is one of the more common geometries. Sometimes when we need to store a tremendous amount of charge, there'll be large containers with insulated oil and plates. And here are your little button capacitors, and again you can see this little helical wire and different contacts. And of course this creates the when we polarize, we get the wire one polarity and the outer casing becomes another polarity, becomes the opposite.